and welcome to this series on physics and philosophy from the University of Oxford. Imagine your favourite football team playing a Premier League final on the same night that your favourite band are headlining at a festival. And you're lucky enough to be offered tickets for both. The decision is tough, so you decide to flip a coin. It lands on heads, and you go to the match. However, later you're left wondering, what if you'd chosen the constant instead? What if the coin had landed on tails? And perhaps it did. There may be a parallel world in which the coin did land on tails, and you did go to the constant instead. The idea of parallel worlds has often been explored in the realm of science fiction. Today, it seems that the concept may be emerging out of modern physics too. I'm Ankita Anirban, and I am speaking to Dr. David Wallace, Tutorial Fellow in Philosophy at Balliol College, Oxford. Dr. Wallace started off as a theoretical physicist, with his first DPhil thesis on relativistic quantum theory. However, his interests in the conceptual and foundational aspects of physics soon led him towards the philosophy of physics, and his second thesis is on quantum theory according to the Everett interpretation. His book, The Emergent Multiverse, was published earlier this year. In this, he discusses the Everett interpretation of quantum mechanics, more commonly known as the many-worlds theory. In your book, you write that the idea of many worlds and parallel universes is an emergent property of the Everett interpretation of quantum mechanics.
Yeah.
Could you please explain exactly what this interpretation is?
Sure. In quantum mechanics, what's going on is something like this. This is our best theory of the very small. It's remarkably effective as a theory, and it seems to say some very strange things about the microscopic world. So it seems to say that atoms aren't just here or here, but they're somehow here and here at the same time, or maybe they're going this way and that way at the same time. And that's weird, but okay, we can perhaps live with the idea that the microscopic world is weird. We're kind of large, slow-moving systems. We're not supposed to find the microscopic intuitive. But the problem is, what the theory also says is that when you look at the microscopic world, that kind of neither this nor that, but both at once, magnifies up to the level of the device doing the measuring. So we don't just have atom here and here at the same time, we have needle on measurement device pointing this way and pointing that way at the same time. And if I look at the measurement device, then the theory says I see this and that at the same time. And that doesn't just seem weird, that seems pathological. It's not clear we can even make sense of the idea of a needle pointing in two directions at the same time. Even if we can make sense of it, then it just seems obvious that we don't in fact see needles pointing in two directions at the same time. So it looks as if something's profoundly wrong with the theory, and the way this is normally fixed in textbook quantum mechanics is just to introduce a new kind of ad hoc rule that says suddenly, when you make a measurement, the rules of quantum mechanics are suspended and we do something different. But no one's ever thought that's a terribly satisfactory way of setting up a scientific theory. And an interpretation of quantum mechanics is a slightly awkward term for a way of sorting out this kind of problem in quantum mechanics and making quantum mechanics a slightly better behaved theory. So perhaps to give some perspective on how the many worlds theory is playing there, you more or less need to see it in contrast with alternatives. So the normal moves other than the many worlds theory you might take, you might call a change the physics move or a change the philosophy move. So a change the physics move says, look, something's clearly broken with a theory. Any theory that predicts that needles are in two places at once or people see two things at once must be wrong, and so we better come up with a new theory that works better than quantum mechanics and doesn't have this problem. Now, philosophers like the change to physics strategy, but physicists don't like it much because quantum mechanics is a really successful theory, and people are really reluctant to change really successful theories unless there's some concrete experimental reason to do so. The change to philosophy theory says, look, all of this confusion is coming because you want to think about your scientific theory as a way of understanding the world, but that's the wrong way of thinking about science. Scientific theories are just gadgets to predict what experiments do. That kind of strategy, if you like, counts as change the philosophy because it's changing the philosophical sense we normally make of scientific theories. Physicists like to change the philosophy theory because it gets them out of awkward philosophical and conceptual puzzles. But philosophers don't like it much because it seems to get in the way of what seems to be a very clear fact about science across the whole of science, which is that the point of science is to learn how things work. It's not that we do science so as to understand what experiments say, it's we do experiments to understand science. So the many worlds theory tries to kind of avoid that kind of dichotomy, and the way it does it is basically saying, look, what would it really be like if a needle was here and here at the same time? What would it really be like if I saw this result and that result at the same time. And the claim is that what it would be like for me to see two results at the same time is for there to be two me's. One seeing one result, one seeing the other result. And what it would be for you to hear me telling you one result and hear me telling you the other result at the same time would be for there to be two yous. One hears me telling you one thing and one hears me telling you the other thing. And so the idea is that when you take seriously the idea that somehow we can be doing two things at the same time and don't just dismiss it as obviously silly, that is, if you think hard about it rather than just appealing to our intuitions, which are a really unreliable way of doing science, then you realise that the quantum theory isn't contradictory at all. It's just telling us something very, very strange about the universe, which is that quantum mechanical processes cause the universe to branch into many, many copies.
So did all these copies of the universe start together at the same time, for example with the Big Bang, or are there new universes being continuously made all the time?
It's more like the second than the first, but this is kind of the place where my kind of, jargon title emergent multiverse comes into play. At the level of the fundamental physics, there's just quantum mechanics. At the level of the fundamental physics, there's no sense of universes at all, of separate classical, as in definite things happening, universes at all. The description of the world as being made up of classical universes is something that happens when we look at the theory at a certain level of approximation. Just as our fundamental physics doesn't contain any chairs or tables. Chairs and tables are a kind of structure inside physics that we observe in certain circumstances and certain regimes. So likewise, the classical universes have that character. But that all being said, the kind of events that cause the world to have the structure of multiple universes rather than one universe didn't happen all at once at the beginning of time. They're happening all the time as quantum mechanical multiplicities get magnified up to classical multiplicities. So every time some process causes a quantum situation that's here and there at the same time to turn into a macroscopic situation that's here and there at the same time, that's when a new universe branching happens. That's not a new law of physics, it's an understanding of what's going on in our existing laws of physics.
So what exactly does it mean for there to be another universe where the alternative happened? Do these universes ever interact with each other? Could I ever find myself in a parallel universe?
They almost by definition don't interact with each other. And what I mean by that is that the reason in quantum mechanics we ever took seriously the idea that somehow the atom could be here and there at the same time was because the here bit of quantum state of the atom interacts with the there bit of the quantum state of the atom. And that interaction is what physicists call interference. And it's the phenomenon of interference that fundamentally gives the experimental results that tell us that quantum mechanics is just fundamentally different from classical mechanics. But it turns out to get this kind of interference between the two places that the atom is at the same time is quite a delicate matter. Doing it with atoms is quite difficult. Doing it with big molecules is really, really difficult. Doing it with viruses is almost impossible, but people are trying. Doing it with entire humans is going to be completely impossible. And what normally happens is that when you make a measurement of the microscopic world, unless you control that measurement incredibly carefully, more and more and more and more systems start ending up in two places at the same time. Again, the jargon term for this is entanglement. More and more entanglement happens. And very, very quickly you get to the stage where there's no prospect whatsoever of interference between the two branches of reality, if you like. That's the point at which we start using the Manyworlds language. So it's not, if you like, that different bits of reality can't interact with each other. It's that the fact that in practice you get to the stage where they're not going to do that is what makes it sensible to start using the language of worlds.
So you couldn't ever experimentally verify this theory in the way that you could experimentally verify other scientific theories?
It kind of depends what you mean by experimentally verify it. Go back to my change the physics versus change the philosophy idea. So if you think that we have three ways of doing quantum mechanics. One is just take quantum mechanics literally, that's the Manyworlds theory. One is change quantum mechanics for a new theory. And one is rethink the way we think of scientific theories. Now you can definitely test the Manyworlds theory against the change the physics way of doing quantum mechanics. The change the physics ways of doing quantum mechanics normally predict that this kind of two things at the same time goes away at some point. And that you can in principle look for. If you were to ever fail to find these interference phenomena where two bits of reality do interact with each other that quantum mechanics predicts are there, if you were to ever fail to find those in a situation where the theory predicts that you ought to be able to see them, that would be a falsification of of quantum mechanics taken literally. So if you like, it would be a falsification of the Manyworlds theory. We'd have to get rid of the Manyworlds theory if that happened. And conversely, every time we make one of those experiments and the result is exactly what quantum mechanics says it should be, that's a situation where we say, okay, quantum mechanics taken literally, the Manyworlds theory has passed that test. Could you ever test quantum mechanics against the change the philosophy idea? No, you couldn't. But that's a very general fact in science. You can never test any theory against the idea that the theory is wrong, but it still gets the predictions right. So to take a silly example, we can test the theory that fossils are dead dinosaurs against the theory that fossils are created by some kind of particular random process, because the theory that fossils are dead dinosaurs makes lots of predictions about where we'd find fossils and how fossils are structured. You can't test the theory that fossils are dead dinosaurs against the theory that fossils aren't dead dinosaurs but behave exactly the same way as dead dinosaurs behave. And that's basically why philosophers don't take these change the philosophy strategies very seriously. They seem to, in some sense, cheat.
So it seems that the Manyworlds theory is the only seemingly valid way of looking at the results that quantum mechanics are providing us with.
I'm always nervous about saying something quite that strong. I think the Manyworlds theory is the only way to make sense of quantum theory as a theory of the world as a whole. It's always sensible to think, well, maybe quantum mechanics is wrong, maybe there's some better theory that we should look for, and I wouldn't in any way want to denigrate the value of lots and lots of different projects to try to do that. But in terms of the quantum mechanics we have, if you want to understand that theory as a theory of the world, not just a convenient black box that tells us what experimental devices will do, then yes, I think the Manyworlds theory is the only way to make sense of it in that sense.
So is it the case that every decision I could possibly make has been made by me in a different universe?
Perhaps it's worth saying a little bit about what these worlds are from our perspective. It's not literally true that the thing that makes these worlds is something like our own everyday decisions. They're made by a particular physical process. They're made by this magnifying up to the classical macroscopic level of quantum uncertainties. However, a great many of the kind of things that determine our ordinary decisions are things that ultimately can be grounded quantum mechanically. So in particular, something like the weather, whether it's sunny today or raining, well, actually at the moment in the United Kingdom that seems to be deterministic, but ideally whether it's sunny or raining does seem to be determined ultimately by very chaotic phenomena in the atmosphere, which is to say very great sensitivity of the atmosphere to its earlier conditions, and that ultimately that sensitivity is powerful enough to magnify up quantum mechanical variations to this level. So yes, there is a branch like this one, but where it's sunny rather than raining. And as in your example where you opened, the fall of a coin is determined by various issues about how exactly one positioned the coin to start with, which in turn you can probably track to quantum mechanical uncertainties magnified up. But there hopefully isn't a branch just like this one in which I spontaneously decide to do something stupid, because hopefully my decision making is determined by some process that isn't just total quantum randomness. So both philosophers and writers of science fiction have an idea of possible worlds which include every possibility as we see it as, if you like, actors, agents. The Manyworlds framework isn't quite like that. It's a bit more tame, a bit more controlled, but it still, in practice, has a lot in common with it. I should also say that the idea of many worlds, although it's been contentious in physics for a long time, now seems to be an idea that seems almost tame compared to some of the other many world stories that have come out of modern physics. So modern cosmology is filled with the idea that we live in a multiverse, a set of worlds which are not just emergent in my sense, but are fundamentally present in the physics. Some of them are even worlds in which the laws of physics are supposed to be different. In many ways, the many worlds in quantum mechanics are a quite tame, well-controlled, well-understood set of many worlds. So perhaps it's not surprising that these days, while I wouldn't say the many worlds theory is a majority view in physics, it's probably tied for first place among the actual interpretations of quantum mechanics that physicists who are interested in this question take seriously.
Thank you very much, Dr. Wallace. Hello, and welcome to the